Imagine light, pure, constant, unchanging. Now imagine that same light being stretched, as if the universe itself is pulling on its very wavelength. It turns red, not because of motion, but because of gravity. This is the gravitational redshift, a phenomenon that confirms Einstein's boldest prediction, that gravity can bend not only space and time, but light itself. Today, we'll uncover the story behind this invisible stretching of light, the physicists who proved it, and how we use it to measure the hearts of distant stars, the motion of galaxies, and even the activity of planets. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. Einstein's general theory of relativity, published in 1915, described gravity not as a force, but as a curvature of spacetime. Massive bodies like stars or planets distort this fabric, and that distortion affects everything, including the frequency of light. When light escapes a gravitational well, it loses energy. But because the speed of light remains constant, that lost energy manifests as an increase in wavelength, shifting toward the red end of the spectrum. Hence, gravitational redshift. Conversely, when light falls into a gravitational well, when it travels toward a massive object, it's pulled to higher energy, compressed toward the blue end of the spectrum. That's gravitational blueshift. This means that color, frequency, and even time itself are relative to gravity's influence. Einstein first predicted the gravitational redshift in 1911, even before his full theory of relativity was complete. But at the time, no one had the tools to measure it. The effect was expected to be tiny, mere fractions of a nanometer, and could only be detected where gravity was extreme. Astronomers soon realized that light from the sun should show a small redshift as it escapes the solar gravitational field. In 1925, Walter Adams attempted to observe this effect from light emitted by Sirius B, a dense white dwarf. His data were inconclusive, but they pointed in the right direction. It wasn't until the mid-20th century that the prediction was finally confirmed under controlled conditions. In 1959, physicists Robert Pound and Glenn Rebka at Harvard University performed a landmark experiment inside the Jefferson Physical Laboratory. They used gamma rays emitted by iron-57 nuclei, measuring the frequency shift as the light traveled just 22.5 meters in Earth's gravitational field. The effect was minuscule, a change in energy of about 1 part in 100 trillion, but measurable. Using the Moosbauer effect, they detected this tiny redshift, confirming Einstein's theory to remarkable precision. The Pound-Rebka experiment stands as one of the most elegant proofs of general relativity, showing that gravity indeed stretches light and alters time. Now that we know gravity changes light, we can use that knowledge to explore the universe. When astronomers look at light from white dwarfs, neutron stars, and black holes, they observe dramatic redshifts. These are not caused by motion, not Doppler shifts, but by gravity itself. For example, light escaping a neutron star's surface is redshifted by nearly 30%, revealing the incredible density and curvature of spacetime near its surface. In black holes, the redshift becomes infinite. Light can't escape at all. This gravitational redshift is also used to test relativity in strong gravitational fields, where Einstein's equations face their toughest challenges. Beyond extreme astrophysical objects, gravitational redshift also helps us measure planetary activity and even calibrate GPS systems. On Earth, the difference in gravitational potential between a mountain peak and sea level causes a measurable redshift in atomic clock frequencies. This means time ticks faster in weaker gravity, a direct consequence of redshift. For spacecraft and satellites, engineers must correct for gravitational redshift and blueshift to ensure timing accuracy in GPS and deep space navigation. Without these corrections, your GPS position could drift by kilometers each day. In planetary science, redshift allows astronomers to detect variations in gravitational potential, revealing internal activity, from the pulsations of stars to the oscillations of gas giants. By studying the tiny shifts in frequency of light emitted from a planet's atmosphere, scientists can infer density, composition, and even volcanic or tectonic activity. If gravitational redshift is light losing energy while climbing out of a gravity well, gravitational blueshift is the opposite. When light moves downward into a gravitational field, say when a satellite observes a signal from Earth, the light gains energy, compressing its wavelength toward blue. This effect is critical for high-precision instruments like the Hubble Space Telescope, LIGO detectors, and space-based atomic clocks. If not properly accounted for, gravitational blueshift could distort readings or mask signals from distant astrophysical phenomena. It's this perfect balance between redshift and blueshift that allows scientists to decode the subtle symphony of light traveling across spacetime. Modern missions like Gravity Probe A, 1976, ESA's ACES clock experiment, and NASA's NICER telescope continue to measure gravitational redshift at unprecedented precision. In 2018, astronomers at the European Southern Observatory observed light from a star passing near the supermassive black hole at the center of the Milky Way, and saw Einstein's prediction play out exactly as expected. Gravitational redshift also plays a role in cosmology, helping scientists distinguish between redshift caused by cosmic expansion and that caused by gravity. It's the foundation for measuring gravitational potential energy on cosmic scales, contributing to our understanding of dark matter and dark energy. Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." Gravitational redshift is proof of that illusion, a demonstration that time, light, and gravity are deeply intertwined. Every photon we observe carries a story, a record of how much gravity it has endured on its journey to us. From the sun's surface to distant galaxies, the color of light reveals the curvature of space itself. So next time you look at the night sky, remember, the starlight reaching your eyes is not just light, it's information bent and stretched by the universe's invisible hand, a cosmic whisper encoded in red. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about gravitational redshift, a phenomenon that confirms Einstein's boldest prediction, that gravity can bend not only space and time, but light itself. Join me next time for another deep dive into the cosmos.